Good morning, everyone. Welcome to another class of CS 2100. Um, okay.
One surface.
Okay. Can you all hear me?
Yep.
Yes? No?
Yes, I can hear you.
Yes.
Good morning, everyone. Can you all hear me today?
Yes, good morning.
Yes?
Yes.
Somebody
Yes.
shake your
Yes.
head, wave your hands, let me know.
Yes.
Okay, good. I'm coming to you, I'm streaming using a different capability with my iPad today because my usual one seems very flaky. So I'm hoping this works well. I can't necessarily. I've got all sorts of noise basically on my speakers for reasons that I can't begin to guess. So I can't set up to answer questions. So if you put them in a chat, then we can get the TA monitoring to be able to, or I can look at it and he can deal with it. So right now I can't hear. If I do that, I get a lot of junk and I don't get you guys. Okay, so I apologize for that problem. And now we're going to try, and if anyone has questions, please put them in the chat right now because I can't, or you can ask them and ask someone else to put them in a chat because I can't deal with having the sound on. I don't hear you. I hear some junk that's coming through beyond my capability of understanding. Okay, so if I well, that's not working, so we'll forget about it for now. Maybe I can. Sorry about that, doesn't work. So let's try and share today and see how far we get. Okay. Someone is asking if you can turn homework in late. Go look and see what it says about turning in homework on the pages. We don't grade homework that's turned in late. I'm sorry. That's one of the things that you were given on the web pages that say something about rules for turning in homework. But if you want to turn it in, then we can see if people can grade it anyway to give you an idea how you did. I'm sorry, but there's just too much going on and the class is too fast to be able to do that. Okay, so lecture 4. Lecture 4, we have all sorts of announcements first, and I want to remind you of this, that quiz 1 is on Tuesday.
And she was
There
just
will
like
be a quiz
talking about other
review
stuff.
session
And then I was just like,
tomorrow,
Emily
Friday.
responded.
Mute
She's like,
yourself,
"Amen,
please."
amen."
led by James.
What did Emily
And
say?
there were enough people who said
She
they
was
would
like that,
come on
we're a
Monday
playgroup now,
morning
and she has a
between
friend
8 and
party at
10.
once.
So Peter will hold one on Monday morning between 8 and 10. Wow, that one is not very clear. Okay, so the grade scope, you were supposed to have done quiz 0 by today. And I hope you got it done, or by tonight. I hope you get it done. The whole idea, there isn't much there to do. You're supposed to read the pledge and you're supposed to read the rules for the exam. And then you're supposed to figure out how to submit it via grade scope. That's the key of it, because you're going to have to do that within a limited time for the quiz on Tuesday. There'll be no class lecture on Tuesday, but from 10:45 to 12:05, you're supposed to be taking the exam. We give you a half hour to upload it, and you're allowed one index question. Now, there will be templates for quiz 1. They are not available yet, but they will be out by Sunday. The reason for that is I can't give you a template before I guarantee I know exactly how many questions are going to be on it. It's not a generic template. It's a different one for every quiz. Okay, continuing. Here you go. Look at the syllabus for the regrading policy. You have to appeal within a week of the score being posted on Gradescope. Regrading for problem sets rarely happens, but you can check it out. Utilize the office hours, Piazza. You have to match the pages to the questions in Gradescope. You can test that out and make sure you understand it when you hand in the quiz 0. Be careful and make sure you do. If you don't, ask tomorrow at the review session. Okay, and remember, you're allowed one 8.5 by 11 page that you have to hand in. No scraps. Okay, I had a few other things. There are some people, for reasons I don't understand, that seem to log into the lecture on Tuesdays and Thursdays. I'm going to set it so that you can't do that, but I'm sorry, log in on Wednesdays and other days. So I'm going to try and set this so that the only times you can be in this Zoom session and taking up my Zoom is during the times that are appropriate, which is Tuesday and Thursday between 10:45 and 12:05. There's a different Zoom that I have posted on the office hours for when I have office hours. So there's a Zoom page for that tells you it's 1 to 3 on Wednesdays generically, unless there's an announcement to the contrary. And that's when I have a separate Zoom link and password. It is true for the office hours for all of the TAs that there is a module that says office hours, and that's in the how to get help section at the beginning, and that will tell you who's there at what time for what office hours. If you, for some reason, you missed the discussion section last week because you didn't know where to look under important links. It lists the TA that is lecturing for that particular time by the section number and by the time. We want you to be able to attend it. Among other things that will happen in the discussion section, this time and also the review session is basically going over some of the questions on the practice quiz. And also, if you ask questions about the homework, that's when you can get your answers. So attend, go, okay? Today, we're talking about some new material with a brief review of some of the work in Chapter 1 that we need in order to do proofs in Chapter 2. So let me remind you from both the pre-recorded lecture 4 and from the book that an implication is something of the form if P then Q, and where P is typically either a proposition or a quantified predicate, which is another form of a proposition, and Q is either a proposition or a quantified predicate as well. So it can be true or it can be false. Okay. Now remember, that's not saying P is Q and Q is true or false. It's saying that the implication itself can be true or false. Okay, let me remind you that if P is false and Q is false, P implies Q is true. I know that's hard to grasp, but it is in fact the case. Okay, the converse of P implies Q is Q implies P. You flip which proposition is in which position. The inverse is not P implies not Q, and the contrapositive is not Q implies not P. The contrapositive is the flip of the converse, and you do a converse and then you take the inverse of the converse, kind of, and that gives you the contrapositive. And the implication and its contrapositive are equivalent. The converse and the inverse are equivalent to each other. Now, equivalent means that the implication is true if and only if the contrapositive is true. The converse is true if and only if the inverse is true. Okay. Wow. So someone asked, what does QED stand for at the end of the proof? Well, to tell you the truth, I don't remember the Latin, but it means you have proved this. QED stands for quo, blah, blah, blah. It's a math term that's used all the time, and it says, this is the end of the proof. I'm finished. I've got it. Okay. Oh, there you go. Quod erat demonstratum. That means that which was to be demonstrated. You finished it. Thank you. Whoever's watching another lecture isn't muted. There's all sorts of stuff coming through there. Yeah. But I can mute everybody, I think. Let me see what I can do here. How's that? So now everybody's muted. Okay. So let's look at a definition review for some of the things that have come up this semester. So the set of integers is represented by that funny Z. The set of natural numbers are all the integers greater than or equal to 0. We note that 0 is defined as a natural number in our book. Some books do not include 0 as a natural number. Z plus and Z minus represent the set of positive integers and the set of negative integers, respectively. 0 is not included in either one. You get 0 as being part of the natural numbers. So 0, the natural numbers is Z plus 0. An integer is even if it can be represented as if there exists an integer k such that that first integer m is equal to 2k. It's called odd if there's a k such that m is equal to 2k plus 1. An integer m is called prime if it cannot be factored. That is, if there do not exist positive integers p greater than 1 and q greater than 1 such that m is equal to p times q. Notice that m has to be larger than 1. There are some books that don't say that, but our book does. Two integers are relatively prime if they have no factors in common. Okay. A perfect square is a positive integer that's the square of another positive integer. Please try and remember that, because we frequently ask questions about perfect squares. And if you don't remember that, then you have a lot of trouble trying to do the problem. So 4 is a perfect square. 3 is not a perfect square. There is no other integer whose square is 3. 9 is a perfect square. Okay, 8 is not a perfect square. And so we can go through. A number q is rational if there exists integers a and b with b not equal to 0, such that q is equal to a over b. There can be many representations for a rational number. It's always possible to choose them so that a and b are relatively prime. So we can have, for example, 2/4, which is 3/6, which is 4/8, and they're all equal to 1/2. And the one that gives us the relatively prime is the 1/2. So that means you can't factor the numerator and denominator anymore and get rid of common factors. So property reviews for integers. Whenever the operations of multiplication, addition, or subtraction are applied to integers, the result is another integer. This is called closure, or we say the integers are closed under that operation. Addition is commutative, multiplication is commutative, subtraction is commutative, division is not commutative, okay? 3 divided by 2 is not the same as 2 divided by 3. Now, so my internet connection seems to be adding to the problem today of being flaky, so I'm apologizing to you. We'll just have to keep putting up with it. Okay. A very important property is the distributive property. Now, in logic, we had 2 distributive properties, but in arithmetic of integers, we have only 1 distributive property. So the distributive property for integers says if you have m, n, and p in z, that p times the quantity m plus n is the same as multiplying m by p, multiplying n by p, and then adding them together. Okay. That's very important and gets used frequently. Notice just 1 distributed property for integers. Okay, here's another one. If n and p are 2 integers, we say that n is divisible by p, or p divides n if there exists another integer q such that n is equal to p times q. In other words, p divides n if p is a factor of q. And we write, notice the order here. It's just written the way you say it. P divides n. This is the one that's a factor. Okay? Sometimes I have seen in the past that on quizzes, students will get the order wrong and that makes the whole thing wrong. So check it out and be aware. The division theorem. We have for all A and Z, and for all B and Z plus. Notice that B has to be positive for this theorem. There exists a Q and Z and an R and Z plus. Here's another one that has to be positive, where Q is called the quotient, 0 is less than or equal to R is less than B is called the remainder, and A is equal to B times Q plus R. I know you had some examples in the pre-recorded lectures. It's important to remember that B and R cannot, well, B has to be positive, R can be non-negative. Note that R can be 0. So if Q is a divisor of A, then R is 0. And otherwise, there's a remainder. So what's the fallout from the division theorem? So integer division, A divided by B equals Q. So that means if you divide 5 by 3, you get 1. Okay, you don't get a real number, you get an integer. It's not rounded, it's 1. A mod B equals R, written also a percent B, A mod B is R, where R is the remainder when A is divided by B. Remember, R is always non-negative, okay? So if you want to ask a question, please type it into the chat because I just can't turn on the sound here. I'm sorry. R is supposed to be 0 less than or equal to R less than what's, no, R is not less than infinity. Oh, you're right. N. Someone said, why did I write Z plus? You're right. That's wrong. It's N. Is that better? Thank you for fixing that. Yeah, okay. So here, this is the correct, it's called the remainder. Good. Are there any other things that I typed wrong? Why does the precedent of the quotient and the coefficient matter? It actually doesn't matter, okay? But you have to remember that R has to be less than or less than B, okay? So you have to know which is the quotient and which is the divisor. There's the divisor and the dividend, and I always have problems here. So it's easier if you order them, but it is definitely not arithmetically required. Okay? Not at all required. But this R, remember, is not something that can be less than or equal to less than Q. It has to be less than B. So you have to remember which one is B. Okay. So in sections 2.1 and 2.2, there are 3 kinds of proofs that have been shown. The indirect is usually by contrapositive, and proof by cases sometimes occur in direct proofs and sometimes in indirect proofs. So we're going to do lots of practice problems next, okay? And here's a reminder that we're going to show in the first few practice problems to help you get started on that. Okay, so here's the statement of the proposition. You have to, whenever you're supposed to prove something, and here's an example, for any rational number R, remember what a rational number is. A rational number can be written as, a rational number Q can be written as A over B, where A is an integer, any integer, and B is an integer that's not equal to 0, usually positive. This is the definition of rational. There you go. So what you have to do is you have to state the proposition. So here you're saying R is in rationals, implies that R plus 1 is in rationals. So then you spell out the properties of the hypothesis. We say then, well, if R is in rationals, R is equal to A over B, where A and B and Z, and B is not 0. Then we express the conclusion in terms of the hypothesis. What that means is we start out and saying, what do we know from the hypothesis? Where are we trying to go? In this proof, it's basically a one-liner. Other proofs take more. So you have to take a few more steps in order to get from positive to negative. So here we go. We say R plus 1 is equal to A over B. We know that from the definition of rational, plus 1. And then we do rational arithmetic here. We say, well, 1 can be written as B over B. That's not its form without any common divisors. Certainly B divides both. And then we do rational arithmetic. Since the denominators are the same, we can add the numerators. Remember, you can only add numerators in rational arithmetic when they have the same denominator. And we get A plus B over B, and that's equal to C over B by rational arithmetic. You take care of details where C is equal to A plus B is in Z by closure of integers. You need to have that. Sometimes you need to say, no, you don't need to say rational arithmetic in your proof. I'm saying it to make sure you understand every step that I do. However, make sure you do your rational arithmetic correctly, because if you don't, then you're not doing it. So that's a reminder to check what rational arithmetic is if you've forgotten it from when you last took math. So we know that C over B by closure of integers under addition. Therefore, we state the conclusion, R plus 1 is rational, and then you would write Q, E, D. Okay? So there are the steps, and we're going to try and use them on the next few examples. Yes, the contrapositive is absolutely true. If R plus 1 is not rational, R is not rational. Okay? So we can prove that, but first let's go through the examples I have, and then we can actually do that. Okay. So we're going to prove if n is even, then n plus 8 is even. So instead of going through this immediately, I'm going to stop for just a couple of minutes and then allow you to try doing this problem. So try filling in the blanks of the proposition, the hypothesis, expressing the conclusion in terms of the hypothesis, if there are any details you need to take care of, and then restate the conclusion. Give it a try. Rational numbers are definitely closed under addition and multiplication. Yes, we could prove that too. Shall we have you prove that? Not this time. We have one we're already proving. That's not one of the propositions that we've had. So that's not definitely one of the definitions. Okay. We'll answer your question about what the notation is shortly. Let's do this proof and then I'll answer it. I don't want to do it on this page because it'll look wrong. Okay, shall we give it a try? Hey, come on, come on. Okay, here's the practice proof, and I've got that so that when you look at it in the notes, you can get to it. So what we do is we state the proposition. If n is even, then n plus 8 is even. And then we spell out the properties. What's the hypothesis? N is even. So we say n is equal to 2m, where m is in z by the definition of even. That's the property of the hypothesis. Now we try and express the conclusion in terms of the hypothesis. So the hypothesis, we look at it and we say, what is n plus 8? Well, we substitution of equivalency. So we put in 2m for n. We have the 8. We apply the distributive property and factor out a 2. So we get 2 times the quantity m plus 4. And that's equal to 2 times c, where c is equal to m plus 4 is an integer by the closure property of integers. And then we take care of we've already got all of the details. In the first proof, we left it. Here we've got them all as part of our step-by-step. So then we say, therefore, n plus 8 is even. Q, E, D. Yes, you will have to name the properties in homework and on quizzes for every step. Thank you for typing them in chat. Yes, yes, that was an absolute necessity. Okay, let's move on to our next one. We have another practice proof. Erase the first one, let's get going. Now we're going to suggest that you do this proof by contrapositive. So for all integers, if n is even, n squared is even, excuse me, then n is even. Okay, so you want to prove the contrapositive. So what would you do here? That's my hint. Okay, prove the contrapositive. It's too easy to make a mistake proving this direct. In fact, it's really hard, but by contrapositive, it's not. Do you always have to restate the proposition? On some problems, you don't, okay? And here's an example where, well, when we show this proof, you'll see what I mean, okay? How many properties are there? What's the list? Well, you have the closure property under addition, the closure property under multiplication. This is for integers. There's nowhere written the ones for rationals. You might have to prove that. You have the distributive property that's definitely given to you. You have the equivalency of substitution. I'm trying to think. And you have the propositions and proofs that are already proved. You have the division theorem. That's a big one. Okay, when you get to proof by cases, that's critical. You will not be given a list of properties and the names you're supposed to call them. If you have any questions, ask me or the TAs, but they're listed in the book. You will not be given a list. We did last time, I think last time, or this time, I think I just went over a bunch of properties and definitions and things that you have. So at the beginning of this lecture, at the beginning of the online pre-recorded lecture. So you've got them and you got them in the book. So they're in multiple places. Okay, are we ready to give a try to this? Just shake your heads, whoever's got your camera on. No, I don't see any head shaking. Yes, yes. Okay, well, we're going to try it now anyways. Okay, thank you. Good. Here's another one. I've got it done for you now so that you can follow it at home. For all of the examples, whether I get to everything today or not, you want to try them before you look at the solutions, and then you can see what you left out or whatever. So here we go. So because we're going to do an indirect proof, we're going to state the contrapositive and acknowledge in it that if the contrapositive is true, the original implication is true by equivalency. So what is that contrapositive? If n is odd, then n squared is odd. Okay, then we go forward. What are the properties of this hypothesis? Remember, we're not doing the original hypothesis. We're doing the hypothesis of the contrapositive here. So we have n is odd, so n is equal to 2k plus 1 for some k in z, and that's the definition of odd. Oh, there you go. You need the definition of odd. Let's keep going. We express the conclusion in terms of the hypothesis. The conclusion says, let's look at what is n squared. So we have n squared. We put in 2k plus 1 for n, and that's substitution equivalency. And then we do the multiplication and get 4k squared plus 4k, 4k plus 1. And then we apply the distributive property and factor out of 2 of the first two terms and get 2k squared plus 2k plus 1. And then we say, oh, well, that's equal, to 2c plus 1. This was actually right. That's equal to 2c plus 1, where c is equal to 2k squared plus 2k by closure of integers under multiplication and addition. Take care of details. So therefore, n squared is odd by the definition of odd. And then you say, we've proved the contrapositive, therefore the original implication that if n squared is even, then n is even is proved. Q, E, D. Okay? So contrapositive proofs, do you have to specify which closure is being performed? That's a good idea. What is the first step called substitution equivalency? Remember, substitution equivalency says that if you have two expressions that are equivalent, namely n is equal to 2k plus 1, you can substitute one for the other without changing the value of the statement. Didn't we just square both sides? Yeah, we did. You can do that. You can say it that way too. Okay. Good. Can we move on? Good. Okay. Another practice proof. Prove that if n is not divisible by 3, then n squared plus 2 is divisible by 3. These are all for integers. Okay. And here's a proof hint to use a proof by cases. Okay. So this is a little bit different than the first two we had. And you have to tell me where you can think of cases or being. Okay. Okay, give it a hit. I'll give you a couple minutes. Okay. Let's give it a try here. This one's a little longer. So the issue is to try and do this using cases. It's the only way you really can get it right. So we're saying n is not divisible by 3. So the division theorem says that for any integer, a, it can be written as some number 3 times q plus r, where r is between 0, less than or equal, greater than or equal to 0, and less than 3. And that's the theorem we're going to use. So the proposition says if 3 does not divide n, then 3 divides the quantity n squared plus 2. That's what we want to prove. We wrote that in math notation now. So the properties of the hypothesis that n mod 3 is 1. Remember, mod means we're getting the remainder here. Or n mod 3 is 2. Since 3 does not divide n mod 3 cannot be 0. So that's the properties of the hypothesis gives us. So we have two cases. The first case where n mod 3 is 1, and the second case where n mod 3 is 2. Okay, the division theorem is fantastically helpful in helping you do a lot of case proofs. So then we go along. If n is equal to 3k plus 1 for some k and z, by what property? The property definition of the division theorem, it basically. I'm sorry, it's, yeah. So then you get, we plug in 3k plus 1 for n, square it, add 2. And you say, can't you just square it and add 2 to both sides? Yes, you can. And we do the arithmetic here, and we get 3k plus 1 all squared plus 2 is equal to 9. Oh dear. Yeah, no, I got this arithmetic right, I think. 9k squared plus 6k plus 1 plus 2. And that's the substitution equivalency in arithmetic. So then we factor it differently, and we're using the associative property when we do that. So we take the first 2 and the second 2 and say we're going to do that addition first. And then we add them together. And then we look at that, the first 2, and we say, I can use the distributive property going from the right side to the left side. And that's basically factoring out a 3. So I get 3 times 3k squared plus 2k plus 1. And then we say, well, that's just 3c, where c is equal to 3k squared plus 2k plus 1 by the closure property of integers. So that tells us that when n mod 3 is 1, then n squared plus 2 can be divided by n. N is a divisor of it. So then we do the second case. Okay, we say n mod 3 is equal to 2. So that means n is equal to 3k plus 2 for some k. That's actually the division theorem, and k is our quotient, remember? Okay, so then we proceed again using substitution equivalency and squaring it and doing the arithmetic. And we get 9k squared plus 12k, and then we're adding 4 plus 2. So those 2 we're adding, and the first 2 we add. And then we look at the whole thing and factor out a 3. That's the distributive property. Told you distributive property is really important. And that's equal to 3 times c, where c is equal to 3k squared plus 2k plus 2 in this case. So 3 divides n squared plus 2. We take care of some details. Well, we don't have any. We got them all as we did the problem. And we state the conclusion. We have shown that for all cases, 3 divides n squared plus 2, and the result is proved. Q, E, D. Yes, you need to state the distributive property. What does 3 divide the quantity? 3 divides n squared plus 2. We just did that definition, and it's in the notes in the book. Means that there exists a k such that, remember that's the such that, n squared plus 2 is equal to 3k, or c, or whatever. Does that help? You can say substitution property, that's okay. Okay, we need our break. Write your question, Daniel. How would you write, for example, that adding 1 to both sides keeps the equation equal? What can I say? I think that that's just plain old arithmetic. I don't think you need to say much to that. Oops, you're right. N squared. Yes, yes, yes. Thank you. Yes, you can say add 1 to both sides. Should k be a variable in both cases? You're doing each case separately and not using the results of one and the other. So since they're separate, they're totally separate proofs, you can use k again, or you can use totally separate variables. If you're not sure, use different ones. Okay? Take your break. Okay. So none of my stuff is working right today. So again, I'm still stuck without being able to have you ask questions. So please ask them on the chat. So I can see you. Someone said by quiz 0, you mean the practice quiz. No, I don't mean the practice quiz. I mean, quiz 0 is the one that you're supposed to, you can access it, the templates for it in Canvas. You have to go to Gradescope. It's actually there, but then you go to Gradescope to upload it. You're supposed to fill it out and practice. Okay, so you can submit it in Gradescope. Quiz 0 is different than the practice quiz. They're not the same things. Okay, so quiz 0 is a pretend quiz that you actually have to download from Gradescope and upload, and the templates for them are both, should be available. If not, let me know. Available through Canvas. So you download them from Canvas. They have a question in it, but it's not a real question. It's just a pretend thing. You fill it out, you read the pledge, you read the rules, and then basically you're going to scan it once you've downloaded it, or if you have it, fill it out online or on your iPads or tablets or whatever, that's fine. And then you're going to upload it back to Gradescope. You're going to submit via Gradescope, and then you have to fill it out of which question is on which page and go through the process so that when you do it on Tuesday, you know how to do it. You're supposed to do it now with this fake thing so you know how to do it. Does quiz 0? Definitely not. Quiz 0 does not affect anything. Okay, quiz 0 is just for practice, downloading and uploading and looking at templates and making sure that you understand, first of all, the pledge that you have to sign, and second of all, the rules of the quiz. It does not count for credit. You say, what if I don't do it? Well, it means you better get it right on Tuesday without any practice. That's what it means. There's no excuse. If you have a problem, now's the time to find out. Ask questions on Piazza. I think Christopher has a question, but you have to write it in chat because I can't turn the sound on. I've got all sorts of junk that happens. Okay. Good. Let's go. Let's do another indirect proof. Okay. For any x in real numbers, remember, the real numbers are composed of the rational numbers that can be written P over Q for integers P and Q, where Q is not 0. And the irrational numbers, and those are all the rest of the numbers in the reals that are not rational, like pi, for example, or like E. Okay, so then we go on. If 2 times x is irrational, then x is irrational. And we're going to let Q prime indicate the irrational numbers. So once again, proving that something is irrational is hard. Okay. Do we have another option? You do. Why don't you give it a try and then we'll do it in class. Will the contract ever change for a quiz or exam, or will they all be identical to quiz 0? They might be somewhat modified. You have to read them and download them every time. You can't download quiz 0. Quiz 0 template is somewhat generic, but every quiz has a different template. Each page, remember, you have to have one problem per page. If you need then more than one page for a problem, you have to add a second page for it. Are rational numbers closed under division? Well, I think that's a great question, and it's something you can prove. That is not a property that's given to you. It is a provable property. I don't understand how you can state X is rational and then try to prove that we don't prove that X is irrational. Okay, I'll tell you. We're going to prove the contrapositive. The contrapositive would say if X is rational, that means not irrational, then 2X is rational. If I'm handwriting and not using a template, should I just provide a signature to take care of the pledge, or should I copy the pledge down and sign? You should print out the pledge and sign it, because you're going to have to scan and upload everything anyway. You don't really want to copy it down by hand. You want to print it out. Do section problems.tech or quiz0.tech. In this particular case for the tech file, I think it's just written as one example, isn't it? What problems in general, in most quizzes, you will type it in problems.tech file. The quiz0.tech file is just sort of the template for everything. And the problems.tech are where it'll print out pages and everything. So that's where you want to put your solutions. Okay, let's prove it. Okay, so the proposition we're going to say is we're going to do the contrapositive. So contrapositive, the equivalent contrapositive is if X in R is rational, then 2X is rational. Okay, so what's the property of the hypothesis? The hypothesis is there exists P, Q in the integers, Q not 0, such that X is equal to P divided by Q. That's the hypothesis. Okay, so we're going to say what's 2X? 2X is then equal to 2 times P divided by Q, which is 2 over 1 times P over Q, which is 2P over 1 times Q by the multiplication of rationals. I'll just say rat. Okay, so then 2X is equal to 2P over Q, because 1 times Q is Q, which is equal to C over Q, where C is equal to 2P, which is an integer by closure of integers. Then 2X is in the rationals because it satisfies the definition. It is written as an integer divided by a non-zero integer. I'm sorry, 2X is in Q, rational. So what do we say? We have proved the contrapositive. So original proposition is true. Q, E, Okay, another one. Oops, well, there's the proof. Okay, another direct proof. Here we go again. For n greater than 4, if n is a perfect, and n an integer, if n is a perfect square, then n minus 1 is not prime. Okay, how can we take advantage of the hypothesis? What does it mean to be a perfect square? Can I go back to the typed version? There it is.
I
Yeah, you
asked a
have to
question.
say it's equal to C over Q because you have to say it's equal to an integer divided by another integer. I'm going to put these notes up this afternoon under class lectures week 2 on the modules. It'll be available there. Okay. H over F can be, yes, H, you can say H, but when you're doing an addition, you have to make the statement that the integers are closed. So you may as well say that C equal to 2 times X is an integer. So it just gets the right form. Okay. How do we prove a number isn't prime? Well, we prove a number isn't prime by showing that it's got factors. It's divisible by two numbers, two different numbers, or two numbers that are bigger than 1. Okay? Okay. How can we show that both factors? That's what I said. We have to show that both factors are bigger than 1. Do you want to give it a try, or shall I just whip along? Give it a try. We've got two things in the hypothesis here. N is a perfect square, and that n is bigger than 4. This is a direct proof. It's not a contrapositive there. Okay. This is pretty straightforward, as someone was saying. N is equal to m squared because it's a perfect square. So we're looking at n minus 1 is equal to m squared minus 1. So we subtracted 1 from each side. And m squared minus 1, as someone noted, is equal to m plus 1 times m minus 1. So we have that as factors. How do we know the factors are not 1? Well, since n is greater than 4, then m, absolute value of m, but m is greater than 2. Has to be, if m, because the only thing that we would have that would be a perfect square, we have 1 and we have 4. And we're bigger than 4, so that m must be bigger than 2. So if m is bigger than 2, m minus 1 is bigger than 1, and m plus 1 is definitely bigger than 1. Okay, so n minus 1 is not a prime. That's the definition up here of perfect square. Most of the rest is just arithmetic. And then this is by the hypothesis n is bigger than 4. Okay? All right, onward. There we have all the nice details. So here are all the theorems and propositions in section 2.1 and 2.2 in the book. Okay. You're saying, do I have to memorize these? I don't know. Some of them are more important than others. Some you can prove. This does not include the definitions and properties that we talked about at the beginning. This is just a summary of everything that's there. We proved this. We just proved that. Let's see, the division theorem we went through, and all the rest of these things are basically, I haven't gone through them before, okay? Notice what we have in 3 and 4 here. This is all integers n. If n squared is even, then n is even. Okay, so look what we have here. We have if n squared is even, n is even. And then in 3, we have if n is even, then n squared is divisible by 4. So what does that tell us? That tells us if n squared is even, it's divisible by 4. We just put those two together. If A, then B, and here we have if B, then C. That tells us if A, then C. Okay? Okay. So we have the specific for any non-zero integer d. If n and n are both divisible by d, then the number m plus n is divisible by d, and the number m times n is divisible by d squared. Every one of these little theorems or propositions are things you should go home and try and be able to prove by yourself. They're all in the book, or else they're all going over either just now by me or in the pre-recorded video. But if you get the grasp and understand how to prove these and use them, then you could do it on a quiz, for example. Okay. Every perfect square is either a multiple of 4 or of the form 4q plus 1 for some q and z. And then there's the division theorem. There. And then we have, if n is any integer not divisible by 5, then n has a square that is either of the form 5k plus 1 or 5k plus 4. This is one that you can use the division theorem on. Remember, we just did one about things not being divisible by 3. So this says not divisible by 5. Aha. Then you can look and say, well, then its square isn't divisible by 5, and you can use the division theorem. Okay, here we have another practice proof. We have time for one more. Well, by gum, this is one of the ones I just said. So this is a direct proof. If m plus, no, it isn't, it's a different one. If m plus n is even and n plus p is even, prove that m plus p is even. And the hint is to use a direct proof. And here I don't have the steps. Give it a try and we'll quickly go over it for our last example. Okay. Here we go. We don't know anything about m and n and p except that they're integers. But we do know that m plus n is equal to an even integer, say 2k, and n plus p is equal to an even integer, say 2j. Okay, so we add them together. I'm sorry, so we know k and j are in z. And then we say, well, then look, m is equal to 2k minus n. We just subtract n from both sides. And p is equal to 2j minus n. So then we go through and we say, well, then m plus p is equal to 2k minus n plus 2j minus n. And we do reassociation. We have that's 2k plus 2j minus n minus n. And we get that that's equal to 2k plus 2j minus 2n. And that's equal to 2 times the quantity, k plus j minus n. So that's using the distributive property of integers, and that's equal to 2c, where c is equal to k plus j minus n in z by the closure property of integers under addition and subtraction. Thus, by the definition of even, m plus p is even. Okay. So this is a little different here. This uses the definition. Then we're looking here and saying, well, how do I write for my proof for the hypothesis? I need Mary plus Peter, m plus p. So we write m and p in terms of what we know. And then we do the addition. Okay, so you have a little step before you can use it directly. All right, with that, I will say, I hope I can fix whatever was wrong by next class. Your exam is Tuesday. I will have templates available to you. I will send out an announcement on through Canvas. Make sure you check your Canvas announcements. I will send out an announcement on Canvas telling you when the templates are available. Okay, with that, I wish you luck. I'm sorry, I can wave to you, but I can't hear you. Good luck on Tuesday, study hard. There's review sessions Friday afternoon and Monday morning. Do well. I want you all to do well.